Here is a small problem. A shop has 12 boxes, 8 pens in each, and it sells 30. How many pens are left? I gave that to a small model and told it to answer right away, and it got it wrong. Then I gave the exact same model, the exact same problem, changed one thing, and it got it right. I didn't retrain it or make it bigger. I just gave it room to think first. So here is the question I want to land by the end of this episode. Why does forcing a model to show its work before answering make it dramatically smarter when it's the same model either way? Nothing about the weights changed between the wrong answer and the right one. The only difference was that one version got to write down its thinking and the other had to blurt. By the end, you'll see exactly why those steps are worth so much. Let's start with something about these models that sounds boring but explains everything. When the model produces a word, it does a fixed amount of work to produce it. The same amount for an easy word and for a hard word, always the same. Think of it as one quick think per token, and that quick think never gets any longer. It doesn't get to slow down and grind on a tough spot, it just does its one pass and hands you the next word. Now look at what we asked it to do in the cold open. We wanted the answer as the very next word right after the question. But getting that answer needs a few steps. Multiply 12 by 8, then subtract 30. We just told the model to do all of that inside one quick think and squeeze the result into a single token. That's like being handed a multiplication and forced to shout the answer before you're allowed to work it out. You could probably do it in your head for tiny numbers, but not for a problem with 3 or 4 steps stacked up. Sometimes it gets lucky, but on anything with real steps in it, one quick think isn't enough and it falls over. So here is the fix, and it's almost embarrassingly simple. Instead of demanding the answer right away, we let the model write down its steps first. We give it a scratchpad and we let it think out loud before it commits to anything. Watch what happens when it does. First, it writes one line. 12 times 8 is 96. That's a small step, well within one quick think, so it gets it right. Then, and this is the important part, it reads its own line back and writes the next one, 96 minus 30. And it lands on the answer 66. The problem it couldn't do in one leap, it just did in 2 easy hops. Here is the mechanism underneath that, and it's the whole idea of this episode. Every step the model writes gets added to what it reads next. So when it works on line 2, line 1 is now sitting right there in front of it as context. It's not remembering 96 in its head, it can't do that, it's reading 96 back off the page. Each written step becomes a foothold for the step after it, and the hard problem gets climbed one foothold at a time. Now I want to clear up something, because it's easy to think reasoning is some new machine bolted on. It isn't. This is the same next token engine we've had this whole course, predicting one word at a time. Writing a step of reasoning is nothing more than predicting the next words, exactly like writing any other sentence. The only twist is what it's predicting on top of its own thinking fed back in as fresh context. Let me say that the other way around, because it's the thing to remember. The model isn't reasoning in some hidden place we can't see. It's writing its reasoning down as ordinary text and then treating that text as more of the prompt. So a reasoning model is the same predictor you already understand, just running on its own output. Thinking out loud isn't a metaphor here. The thinking literally is the output, and the output literally is the next input. So if any model can do this, what makes a proper reasoning model? It's how we train it, and this connects straight back to the last episode. Remember, we taught models to prefer answers people like by rewarding the ones they picked. Reasoning training does the same shape of thing, but with a cleaner kind of reward. We take problems where we actually know the right answer, like math or code that either runs or doesn't. We let the model try each one many different ways, writing many different chains of steps. Some of those chains stumble into the wrong answer and some of them land on the right one. Then we simply check the final answer against the truth and keep the attempts that got there. No human has to judge the thinking, we just ask, did it land on the right result, yes or no? And we nudge the model toward the kinds of steps that tend to reach the check mark. Do that across huge piles of checkable problems, and something quietly remarkable happens. The model teaches itself to write longer, more careful chains of steps, because those are what earn the reward. Nobody handwrote the good reasoning for it to copy. It found its own way of thinking that reaches right answers just by being rewarded for reaching them. That's what turns an ordinary predictor into a reasoning model. There is one more lever here, and it's a strange, powerful one. Once a model can reason, you can just let it think for longer. More steps on the scratchpad means more of these quick things spent before it answers, and we call that test time compute. It's compute the model spends while it's answering you, not compute we spend training it. And within reason, the more of it you allow, the harder the problems it can crack. But watch the curve, because it isn't a straight line up forever. At first, letting it think more helps a lot, and the accuracy climbs fast. Then it bends and flattens out, and past a certain point extra thinking buys you almost nothing. There's a sweet spot, enough room to work the steps without rambling for no reason. So thinking longer is a real dial you can turn, it just has a ceiling like everything else. So let's answer what we started with. Why does the same model get dramatically smarter just by showing its work? Because it only gets one quick thing per word, and a hard answer needs more thinking than one word allows. When it writes its steps first, each step is an easy one, and each finished step becomes context it can read for the next. And it's still the same next token engine the whole way, just feeding on the thinking it wrote a moment ago. The model didn't get smarter, we just stopped forcing it to think in a single leap. And notice we quietly assumed the model writes down one fixed chain of steps. But at every single word, it's actually choosing from many possible next words, and that choice can go different ways. Next time we open up that choice and see why the very same prompt can give you a different answer every time you ask. That's where thinking meets chance.